All right, let's dive right in. Welcome, everyone. Today, we are tackling a fundamental topic that is an absolute favorite for tech interviewers, and that is the singly linked list. Now, in this explainer, we aren't just going to sit here and memorize abstract concepts. No, our goal today is to completely master both the underlying logic and the exact Python syntax you need to build this data structure completely from scratch. I am super pumped to unpack this with you all, so let's get started. But before we even look at a single line of code, let's talk about the real world for a second. You might be wondering, where do we actually use these things? Well, think about Spotify. When you hit play next and queue up a song, or even when you just click the back and forward buttons in your web browser, what is actually happening behind the scenes? Believe it or not, what you're interacting with are real-life implementations of linked lists. They are literally everywhere in practical development.
So here is our roadmap for the explainer today. We're going to cover 1, the need for linked lists, 2, the anatomy of a node, 3, the Python syntax setup, 4, inserting elements, and 5, deleting elements, along with some tricky edge cases.
Kicking things off with Section 1, the need for linked lists.
Okay, so why do we even need them? This comparison brilliantly illustrates the core difference between arrays and linked lists. While Python lists kind of handle memory management and resizing under the hood to make our lives easier, traditional arrays demand contiguous, meaning continuous, blocks of memory. And that's a problem, because if you make an array too big, you're wasting memory. If you make it too small, you completely run out of room. Linked lists, on the other hand, give us the incredible freedom of dynamic sizing and non-contiguous memory allocation at runtime. Basically, this means we can just grab available memory blocks from absolutely anywhere in the system, whenever we need them, without needing them to be right next to each other. It's a total game changer.
Moving right along to Section 2, the anatomy of a node.
To understand a linked list, you have to understand its core building block. Because linked lists allocate memory dynamically at runtime, these blocks of memory don't just have standard, easy-to-remember variable names. Instead, we have these dynamically allocated blocks called nodes. You can think of a node as the essential, fundamental building block of your entire list.
Now, take a look at how this is structured. Every single node is split into 2 very distinct compartments. The first part is the data. This could be a string representing a song title, like Bohemian Rhapsody, or maybe just a simple integer value. The second part is the next compartment. This is absolutely vital. It's the memory address that points directly to the next connected node in the chain. It's honestly like a treasure map, where each chest you find tells you exactly where to go to find the next one.
All right, Section 3, Python syntax setup. Let's look at the code.
Before we write anything, let's just use this as a quick translation guide. In Python, class means we are creating a custom, user-defined data type, which we need since a node doesn't actually exist by default. In it is our constructor function. That's what allocates the memory and initializes our variables. And self? That just acts as the pointer referencing the current object we are working with.
So, let's look at the exact Python syntax. Here we define our class node. Inside that, our __init function takes self, info, and a default parameter of next equals none. We set self.data to the information that gets passed in, and self.next to the next address. I want to point out that the default next equals none part is brilliant, because when you first create a node, it isn't connected to anything yet. It is just floating out there in memory, completely alone, waiting to be linked up.
And to navigate those floating nodes, we really need to talk about pointers. I absolutely love this metaphor for it. The head is the boss who never moves. The temp pointer is the assistant who does the walking. You see, the head pointer absolutely must stay anchored at the very first node. If the head moves, you literally lose the start of your list forever. It's gone. So when we need to travel down the list, we spawn a temporary pointer, an assistant, to do all the actual walking for us.
Knowing that, we can now initialize the overarching linked list class itself. We define a class singly linked list, and in its constructor, we simply set self.head equals none. This creates a brand new, entirely empty list, where the boss, the head pointer, currently has 0 nodes to manage. Definitely keep this concept of an empty list in the back of your mind, because we are going to need it for some edge cases later on.
Which brings us to Section 4, inserting elements.
Let's step through the algorithm for inserting a node at the very end of the list. First, you dynamically create a new node. Let's say it has a target integer value of 42. Second, if the list is empty, your head pointer just points directly to this new node. Done. But if there are already items in the list, our assistant pointer, let's just call it T1, traverses the nodes until it finds the one whose next is none. Finally, we take that last node's next compartment and point it to our brand new node holding 42. Pretty simple, right?
But what if we want to insert a node right in the middle of the list? Okay, here is where it gets slightly tricky. Our assistant T1 traverses until it finds the target data we want to insert after. Then, we absolutely must point the new node's next to T1's next before we change T1's pointer. Let me repeat that because it's crucial. Step 2 must happen before Step 3. If you point T1 to the new node first, you completely overwrite and lose the memory address of the rest of the list. It literally just vanishes into the void. No way to get it back.
To solidify that logic, here is the exact Python syntax you'd use. First, temp.next equals t1.next. This builds our new bridge to the rest of the list. Only after that safety net is securely established do we say t1.next equals temp, which essentially burns the old bridge. This perfectly inserts our new node right in the middle without breaking the chain.
Finally, Section 5, Deleting Elements and Edge Cases.
Breaking down the deletion logic, you'll immediately notice a new challenge. Because this is a singly linked list, we can only go in one direction. We cannot go backwards. So when our assistant T1 is searching for the target value to delete, we actually need to introduce a second pointer. We'll call it previous, and it follows exactly one step behind T1. When T1 finds the target, we simply tell previous.next to point to T1.next. This elegantly bypasses the target node entirely, which effectively deletes it from our chain.
But wait, hold on. Think about this for a second. What if the element you want to delete is the very first element, the head? In that scenario, there is no previous node to do the bypassing. So how on earth would you handle that?
Well, here is a little insider knowledge for you. This is exactly what interviewers care deeply about. Pretty much anyone can write a basic while loop, but identifying and handling these specific corner cases, that is the secret to passing tech screens. You have to account for deleting the head, which literally requires moving the boss pointer to the next node. You have to account for deleting the last element, where you must tell the second to last node to point to none. And of course, you absolutely must handle an entirely empty list without crashing your whole program. And here is the highly satisfying, elegant Python solution to handle those exact edge cases. If the head needs deletion, the boss simply takes a step forward. Self.head equals t1.next. If the last node needs deletion, we just write previous.next equals none. By integrating these quick checks before and after your main traversal loop, your linked list code becomes practically bulletproof.
Well, we have covered a ton of ground in this explainer today, mastering the syntax and the logic of singly linked lists in Python. But I want to leave you with one final provocative thought. We know singly linked lists only move forward, right? If you were an engineer tasked with optimizing this so a user could efficiently traverse backwards, say for that browser's back button we talked about at the very beginning, how would you redesign this node? Think about that, because it is the perfect stepping stone into our next logical leap, the doubly linked list. Thanks so much for joining me on this explainer, and keep coding.